So anyway, the intermediate value theorem, that's what we were talking about last time. And at the very end, I wrote down this very fancy, sophisticated way of thinking of the intermediate value theorem. And it says, if f is continuous and E is a connected set, then f of E is connected. This is a fancy way of stating the intermediate value theorem. And the picture you should have in mind is, well, a connected set in the domain like this. When you do a continuous function to it, the graph looks something like that. And the range values is also connected. That's what the intermediate value theorem says. Specifically, there is no gap in the range, right? If there was like a hole in the range, this would be a violation of the intermediate value theorem, because that would mean there are some y values which just never are assumed by the function, but that's not the case. The intermediate value theorem says if you have any two y values, then all the ones in between them have to be other parts of the range, all right? This is the picture to have in mind. I decided I was gonna put this off until after the test, but I figured we might as well do it because actually we haven't talked about connected sets for a while, so I thought it might be a nice little review about what connected is all about. And the first thing that you should remember about what connected is all about is it's much easier to talk about what disconnected means than it is to talk about what connected means. Like, the definition of connected is basically the opposite of disconnected. And disconnected means you can cover it with two sets that have some properties. So actually, rather than prove this directly, we'll prove the contrapositive. It's easier just to get a handle on because it's easier to talk about disconnected rather than connected. So we'll prove the contrapositive. Can anyone say what's the contrapositive statement here? Remember, like P implies Q, the contrapositive would be not Q implies not P. Yeah? Uh-huh. Yeah, so actually I want to just take this part. So let's stay with f being continuous. So how about, I'll write it differently. I'll say it this way. Let f be continuous. And then now this is the contrapositive that I was talking about. If f of E is disconnected, then E is disconnected. Right? This is what we're gonna do. It's just easier to get started if you're assuming that something is disconnected rather than assuming that something is connected. All right? On the picture, by the way, this is the E, right? And this is the f of E. E is the domain set, and f of E is the corresponding set in the range. All right, let's see if we can do this. So I'm going to say let f be continuous and f of E disconnected. All right, so actually I'm going to draw another picture, but this time I'm going to draw the picture when f of E is disconnected. It's like this, right? F of E, the range is somehow in two separate parts, all right? And then I have my function. I don't really even know how to draw the function that graph of the function apparently is not accurate because the range is actually in two pieces. This, of course, is not possible with a continuous function, but all right, f of E is disconnected. Anyone remember, what does that mean? This disconnectedness? So, anybody remember what disconnected means? Yeah.
That it contains a separation.
Yeah, that's right. And what does that mean? That's really what I wanted to get at. That's the thing about there's two sets where something. Yeah.
Would be like the union of the first part, so like F E1.
I'm going to call them A and B.
Okay,
Is that all right?
So the union of A and B does
Uh-huh.
not equal B.
I'm saying it's disconnected, so that means that it is a union of two separate parts where those parts have certain properties.
The intersection is
Uh-huh. The intersection is empty? The intersection of what exactly? Some technicality here. You remember?
Isn't it you have to do the closure of one
Yeah.
and the other?
Yeah,
and then
right.
do the opposite of the other closure?
Yep. So A bar intersect B is empty, and also A intersect B bar is empty. So this, I hope you know, by the time the test comes around, I hope you remember this definition. This is what disconnected means. You can write it as a union of two sets, and those two sets are disjoint in their closures. A closure intersect B is empty, and A intersect B closure is empty. All right, so on our picture, I guess, you know, this is what the A and the B are. They're up there, all right? Now, we have to somehow demonstrate that the domain set also must be disconnected. Actually, in that case, it would work out. Like the picture would actually make sense if we had two separate pieces here, and maybe my function was like this, just like somehow the domain was actually in two separate pieces. And then this picture would make sense, even if the function is continuous. I don't know if you look at this and think, isn't that discontinuous? But on the domain, this is continuous. For all points in the domain, it's continuous at all of those points. If these points in the middle just aren't part of the domain, that still would count as continuous. All right. Anyway, we need to demonstrate that E is disconnected. That's where we're going. So in order to do that, we have to say what are the two pieces of E, right? So to demonstrate E is disconnected, you must write E is equal to A union B, but I'm not going to call it A and B anymore because I already have a name for that. I'm going to try and call them like C and D, right? They are meant to be these two parts of the domain, and we have to say what they are. C, I'm going to define to be all of, I mean, you can tell on the picture what C has to be. C is all the points in the domain where the function maps them into A, all right? This would be, you can write this as, it's all x in the original domain, which is E, such that f of x is in A, right? All the points whose image is in that set A. That's what I'll call C. There's actually another way to write this. Anybody remember this? I'm sure you talked about it in your discrete math class. All the points in the domain which map into A. This is also written as the pre-image of A, or the inverse image of A. This, well, it's E intersect with that, if you like. I don't know if you like writing that. Remember, F inverse of A means all points such that f of x is in A. I put E intersect because I'm also requiring that x is in E. All right, anyway, that's how we write the definition of C. And then D is the same but with a B. So D is x in E such that f of x is in B, all right? And we must explain why C and D actually are a legitimate separation. That is to say, these weird properties with the intersections are true. So I think it's clear enough. You can tell that so E really is the union, C union D, because this is a B here. Either way, we're taking the points from E. They either go into A or they go into B. And so the E really is the union of these two sets. All right? And what about the intersections? So we must check, and hopefully this will work out nicely. We must check that C bar intersect D is empty and C intersect D bar is empty, right? And I think this is easiest to do with a little contradiction. So let's assume, and we have to prove both of these, but they really go the same. Let's just assume that this first is not true. So for the sake of a contradiction, I'm going to assume that X is in C bar intersect D, all right? And hope somehow I want to get a contradiction from this. So this means that X is in C bar and also X is in D. So I can say, first of all, this is the simpler thing. Since X is in D, that means that f of X is in B, right? Because that's what the definition of D is. It's all the points here where the value of the function sends it into B. And then also X is in C bar, all right. Since X is in C bar, now this does not necessarily mean that f of X is in C. It means that X is in the closure of C. It is either in C or it is a limit point of C, all right? Since X is in C bar, can I just say what I said there? Either X is in C or X is a limit point of C, right? And what that means, X is in C means that f of X is in A, because that's the definition of A. If X is a limit point of C, here I'm going to breeze over a few little details, but this here means that f of X is a limit point of A. And this is the only time in the proof where we use the fact that f is continuous. If X is a limit point of C, that means there's a sequence of values in C which lead to X. And since f is continuous, you can apply f to the whole sequence. And the answer you get will be a limit point. All right. So anyway, the second part says, since X is in C bar, either f of X is in A or f of X is a limit point of A. That means f of X is in the closure of A, because either it is one of those points or it's a limit point. So I'm past my 10-minute limit. Sorry. We're almost done here. So f of X is in A bar, right? Because we said it's either in A or it's a limit point of A. That means it's in the closure of A. That's what the closure is. It's all of A plus all the limit points. All right, I'm trying to get a contradiction. Anybody see a contradiction here? Actually, it's all laid out before us. Yeah?
Yeah, that's
Uh-huh. Yes? So we got this and this. Why is that a contradiction?
because we said the union of that is
Yeah, we said before that the intersection of A bar and B, way up here, A bar intersect B is empty, but we've just demonstrated some point which is in both A bar and also B. So that's the contradiction. So I will just finish. So f of X is in A bar intersect B. And this is a contradiction with the fact that A bar intersect B is empty. Yes?
Does that imply, like, that we have to be connected, that was that contradiction?
Yeah, right. Yeah. Yeah, in order, so this thing, which I assumed to get the contradiction, this would imply that that the range is also connected. Yeah. All right, that was 15 minutes. I thought it was a, I don't know if the whole proof seemed, I don't think it's necessarily an easy proof, but I want to do a little, I suppose, review of, just to remind you all of what connectedness is all about. And the fact that it's easier to handle disconnectedness than connectedness.